and welcome to Alpha Omega training videos. In this video we are going to simulate the blood flow in a clogged artery using ANSYS Fluent software. After that we will extract the results related to some defined or available parameters in the simulation. Stay with us. At first I open the ANSYS Workbench software, and here in the project schematic window you can see the geometry which is drawn in the design modeler software. After that, the geometry is imported into the meshing software, which is ANSYS meshing, and the mesh file is imported into the ANSYS Fluent software, and there it is solved. Okay, let's take a look at ANSYS Fluent, ANSYS meshing software. Here in this software you can see a wide variety of different options and tools to generate a high quality mesh for your geometry in order to import it in CFD simulation softwares. Okay, this is the geometry. By clicking on the mesh you can see the geometry and elements of the surface. By opening the mesh, here you can see that a face sizing, a sweep method, and an inflation are defined to generate this mesh. Here by right clicking on the mesh and insert, you can see the different tools available for us to generate elements. Here under the mesh we have the named selections, one inlet, the walls, and outlet. These named selections will be our boundary conditions in the ANSYS Fluent software. Okay, here we can check the quality of our elements in front of under the quality, and in front of the mesh metric we can change the none to, for example, aspect ratio. Alright, the aspect ratio refers to the ratio of the longest edge to the shortest edge in a cell. It's an important metric for mesh quality. Fluent can handle high aspect ratio cells, but for better accuracy, it's recommended to keep it below 100. The next parameter could be orthogonal quality, and in this case, the orthogonal quality is a measure of the cell's deviation from a perfect shape. The range is 0 to 1, where 1 represents a perfect cell. Lower values indicate poor quality, potentially leading to inaccurate results. It's crucial to maintain high orthogonal quality perfectly above 0.1. And the last option, which is statistics, here we can see the total number of elements, which is more than 400,000. Also, you can zoom in the YZ plane, and here I can draw a section to take a look inside of the mesh file. Here we can see that there is a beautiful structured elements inside the geometry. Alright, let's close the ANSYS meshing and enter the ANSYS Fluent. To enter the ANSYS Fluent software, here I double click on the solution and edit. Alright, the software is loaded successfully. Here you can see the geometry of the solution. Here, by clicking on the display mesh option, you can select the boundaries you want to display. Also, you can check your mesh file. It's done. Make sure that the minimum volume is not a negative value. Also, you can report the quality of your elements, which we talked about in the ANSYS machine software. In the info size, here the total number of cells are visible. And also we can take a look at the surface elements by enabling the edges. Alright, the after the mesh section we have the solver, which its type is pressure based. The pressure based is primarily used for incompressible and mildly compressible flows. This solver uses a pressure correction to solve the Navier-Stokes equations. The steps involved include guessing the pressure field, solving the momentum equations to obtain a velocity field, and then correcting the pressure field based on the divergence of the velocity field. The process is then iterated until a converged solution is found. This solver is efficient and suitable for a wide variety of flow problems. Okay, the velocity formulation is absolute, and in case of time, the solution is steady state. Also, the effects of the gravity are neglected. After the general, we have models. Let's dive into the fascinating world of ANSYS Fluent models. ANSYS Fluent is a powerhouse of computational fluid dynamics models. It includes turbulence models to simulate the chaotic motion of fluids and multiphase models for scenarios where different phases of matter interact, but that's not all. Fluent also offers heat transfer models for thermal analysis and reaction models for chemical reactions. Need to simulate combustion? No problem. Fluent's combustion models have got you covered. And if you're dealing with species transport, Fluent's species transport models are at your service. All these models are designed to help you simulate the most complex fluid dynamics problems with ease and accuracy. So get ready to unlock new levels of understanding with ANSYS Fluent. Okay, in this problem, we just use the viscose model, which as you can see is selected as K epsilon and realizable. This model offers an improvement over the standard K epsilon model, which is a two equation turbulence model, by providing superior performance for flows involving rotation and boundary layers under a strong adverse pressure gradient, separation, and recirculation. The realizable K epsilon model is based on the transport equations for the turbulence kinetic energy and its dissipation rate. The term realizable means that the model satisfies certain mathematical constraints on the Reynolds stresses consistent with the physics of turbulence. The benefits of using this model include its robustness, economy, and reasonable accuracy for a wide range of turbulence. After models, we have the materials. Here, by double clicking on the materials, we can see the fluid and solid, which the blood is defined for the fluid and aluminium for the solid. Okay, by double clicking the blood, we can see the density and viscosity defined for this material. Also, to access to the Fluent database materials, you can hit this option, and here you can see a bunch of materials predefined in this software. You can change the fluid to solid, and here are the solids. Alright, then we have the cell zone conditions. Here we have one zone, which its name is solid, and here we can define frame motion, mesh motion for rotation of a part of a specified part of a domain, which is not necessary for our in this simulation. A laminar zone, porous zone, a 3D fan zone, or different source terms and fixed values. Okay, leave this section as default, and let's go to the boundary conditions. Here in the boundary conditions we have inlet, interior, outlet, and wall boundary condition. Let's enter the inlet. For the inlet, the type is mass flow inlet, and inside it, in the mass flow inlet window, the mass flow rate is selected and entered by this value, and this is the turbulence section, which turbulence intensity and turbulence viscosity ratio should be defined. Leave this section by default and enter this value for the mass flow rate. Next, this is the interior section, which is the internal section of our domain, and there is no option to modify. Also, for the outlet boundary condition, just make sure that the gauge pressure is set to 0 Pascal. For the wall boundary condition, the wall motion is set to stationary, and also the shear condition is no slip condition. Alright, the setup section is finished, and let's go to the solution in the next step. Alright, in case of a solution section, we have the methods. In the methods window, we have first the pressure velocity coupling schemes. If you open the schemes, you can see the simple, simple C, piezo, and coupled. For this tutorial, the simple C method is used. The simple C, or the semi-implicit method for pressure linked equations consistent in ANSYS Fluent, is a pressure velocity coupling method used to solve Navier-Stokes equations in computational fluid dynamics simulations. This method is an improved version of the simple scheme, offering faster convergence and better stability. It is particularly effective for low speed incompressible flow simulations. Simple C iteratively solves the momentum and pressure based continuity equations until a balanced flow field is achieved, making it a vital tool in CFD analysis. Okay, after that we have the flux type. The flux type is select as momentum based, while we have the distance based against it. The right show momentum based and distance based flux type are used for pressure velocity coupling in simulations. The right show momentum based flux type is the original method, which is used to avoid the checkerboard pressure pattern by introducing a momentum interpolation term in the pressure equation. It works well for structured grids and also unstructured grids. Under the spatial discretization, we have some options, which the first one is a gradient. For the gradient, least square cell based is selected. This option is an approach used to calculate gradient vectors for scalar quantities in the flow field. The method works by minimizing the sum of the square differences between the values of the scalar quantity at the cell centers and the values predicted by the linear approximation of the scalar quantity over the entire cell. Next, we have the discretization method for the pressure. For the pressure, we have different options such as second order, standard, Presto, linear, and body force weighted. Presto, or the a pressure staggering option method in ANSYS Fluent is a pressure interpolation scheme that is often used for flow problems where the pressure field is of particular interest. This method provides a more accurate representation of the pressure field compared to other methods, such as the simple or piezo methods. Presto is especially useful for simulations involving highly swirling flows, compressible flows, and flows with large pressure gradients. After that, for the momentum, turbulent kinetic energy, and dissipation rate, we have selected the first order upwind methods, while we have the second order, quick, and third order for most accurate solutions. Under them, we have the pseudo time method, which is selected as local time step. What is local time step? The local time step, or LST method in ANSYS Fluent, is a powerful tool that enhances the speed and convergence of transient simulations. Transient or steady simulations. The LTS method allows the solver to use different time steps for different cells in the computational domain. This means that regions with high dynamic activity where the flow variable changes rapidly can be computed with smaller time steps, while regions with less activity can be computed with larger time steps. Okay, after that we have the controls, and in the controls we have the under relaxation factors. URF is a numerical technique used to control the convergence of the solution in iterative methods. It's a factor by which the computed change of a variable is scaled down to avoid potential divergence or escalations in the solution process. The range of under relaxation factors varies between 0 and 1. A value close to 0 means that the solution will converge slowly, while a value close to 1 means that the solution will converge faster, but it may lead to instability if the value is too high. After that, we have the report definitions. In the report definitions, user can create various types of reports such as surface reports, volume reports, force reports, flux reports, and other different reports. These reports can contain information about the flow field like pressure, velocity, temperature, and more on a certain boundary conditions of the solution. After that, we have the monitors. If you open the monitors, the first option that you can see is residuals. The residuals represent the imbalance in the solved equations and are used to assess the convergence of the solution. When the solution is perfectly converged, residuals would theoretically be 0. However, in practice, due to numerical errors and approximations, residuals tend to reach a small value and then level off. Here you can see the absolute criteria of each of the equations, which under this amount the equations will be converged. Make sure that the print to console and print or plot options are enabled. Okay, before going to the run calculation section, we need to initialize our solution. Initialization defines initial conditions for the computational domain, setting the starting point for the calculation. Standard initialization sets uniform conditions, while hybrid initialization uses potential flow solutions to initialize the flow field, useful when the initial state is not well known. But here we can select the standard initialization and compute from the inlet boundary. Here you can see that the x velocity is approximately 1 and y and z velocity are close to 0. We can change them to 0 absolute value, and here are the turbulence kinetic energy and dissipation rate. After that, if you initialize the solution, it will be ready to run. Okay, after that, let's go to the run calculation section. Here enter the number of iterations. Alright, what is the iteration in ANSYS Fluent software? The iterative mode of a calculation is a critical process that is used to solve complex problems in a step-by-step manner. The software divides the problem into smaller, manageable parts and solves them iteratively until it reaches the final solution. This method is particularly useful when dealing with nonlinear problems, where the solution is not directly proportional to the input. The software continuously refines the solution in each iteration, providing a more accurate and precise result. The iterative method also allows for better control and monitoring of the solution process, enabling users to make necessary adjustments to achieve optimal results. Okay, after hitting the calculate, the solution will start to get solved, and in the next section we will investigate the results achieved. Alright, finally after a few minutes the solution is stopped after 1000 iterations which we entered here. Alright, here you can see the residuals relevant to each of the equations which are written here. So to extract the graphical results under the results section, we can open the graphics, and here we have the contours. The mesh section is for displaying the geometry and mesh file. In the contours, we can display the contours relevant to different parameters. Here you can see the velocity magnitude in a central plane defined in the surface section, plane 8. Alright, we can change our parameters to, for example, pressure. And here the variation of the pressure value is interesting in the plugin section. There are different other parameters such as turbulent kinetic energy and turbulent intensity and a lot more. Alright, let's go to the next section, which is the vectors. I want to take a look at the vectors available on the plane 8 colored by velocity magnitude. I can decrease the number of vectors, scale down them, alright. By entering the vector options, we can select the fixed length, apply, and set. It's not a suitable view, so we can decrease the scale value again. And this is much better. You can also go to the scene section. Here the geometry is selected and vector, save and display. Alright, here you can see the mesh file and the contour is inside it, but we can increase the transparency of the mesh file, and now at the same time we can see the elements, the geometry and the vectors inside it. The next option could be the path lines or streamlines released from the inlet boundary condition and colored by pressure, for example.